Okay, so today we're gonna go a little bit more into this idea of, or more into probing this Schrödinger equation. Remember, this is the Schrödinger equation with just some reparameterizations. I wrote everything down again here. This was our initial reparameterization given the potential that modeled an oscillating system. And we defined its canonical momentum. And so these are canonical. These are what are called canonical variables. Canonical variables. And these are the operators. So here we have our creation and annihilation operators. They form this algebra, or this commutator. Remember, this is an algebra. We kind of went over already what a commutator does. It sort of defines the relationship between elements within a very specified algebraic structure. And so what we get is the commutator. So we have the commutator between the creation and annihilation operators is a real number, unlike the canonical variables. And then and then we also were able to show these guys right here, which were these operators in terms of P and Q, right? So these are the operators. Now, this is another operator. This is different though, because this is kind of interesting how we build this up. See, we are going from we take these canonical variables, right, and we can write them and then these things encompass these canonical variables inside of them, and these are operators, and then this is the operator that encompasses the sort of these operators, these raising and lowering operators, and this is what we had. We can also show that h bar is also equal to, let's see here. I won't prove this, but it's not too terribly difficult to prove this. And that should be a plus, that should be a minus, like that. So, actually, am I getting that right? Yeah, I think I am. Okay. And so we have this right here. So given these two, given all of this, we can now be able to find what exactly something like this would look like. So these are two elements. These are two elements that we're binning into an algebraic structure. We have the Hamiltonian and the lowering operator. Right, so what does this look like? And this is a commutator between the two. So this looks like h bar omega. So I'm just literally plugging everything in here. And I'll do a dagger minus 1/2. And then commutated with a. Right, so this here is h bar, or our Hamiltonian. And this is our annihilation operator. And this is equal to h bar omega times a dagger minus 1/2 times a. Because these are constants, right? Whenever you can go to any online source and you can find that we can pull constants. This is a property of the commutators. We can pull constants out of the commutator, and then so this becomes so we could break this up even more. This becomes h bar omega a dagger commutated with A minus 1/2 commutated with A. Right. And this here is actually going to be, this is going to be 0 right here, because this is just a number, right? This is a number, and what we're going to get is we're going to get 1/2 A minus A 1/2. Well, A times 1/2 is just 1/2 A, and so this is going to be 0 because of this constant right here. So I'll do a different color to cancel things out like I've normally been doing. And so what we get now is this, that this is equal to, now I'll do this commutator right here. So this is h bar omega. And so this commutator is a dagger, A minus a dagger. A lot of A's going on here. These are just, remember, these are just creation annihilation operators, and those are these guys right here. All right. Okay, so I'm going to put a pause on this really quick because I want to take a look at what this guy equals right here. A times a commutator of a dagger with A plus A commutated with A times A. So this equals A, and this is our commutator right here. So that's going to be A dagger, A minus A dagger plus 0, because again, this commutated, anything commutated with itself is going to be 0. So this is plus 0. All right. And lo and behold, what you see that we get is A dagger A minus A dagger. And actually, I'll get rid of that parentheses right there, because that's going to be like that. And we have an A dagger right there. And so this right here is this, right? So we can rewrite our Hamiltonian as h bar omega as A dagger with A plus A okay, and then this here we said was 0, and so this is this is 0. This here we said was 1. Bring a different color. This here is 1. So what we get, actually that's -1, because this is the opposite order, if I remember correctly. Anything in opposite order commutator. A dagger. I think I might have missed a negative in here somewhere. But this, yeah, so this becomes -1. And that becomes negative omega, h bar omega A. Now, let's see it. This is -1. Let me just double check. I think this sort of depends on how we define our P, remember? I think I might have missed a negative somewhere in there, but what we see is that if we define P in this way, if we define P in this way, dq, then we get this right here. Right, and so I will rewrite this. This is negative h omega a, and same thing here. We have h bar a equals positive h bar omega a dagger. And these are the two, and we can prove this one to ourselves too, using the same process. Right, so these guys right here form an algebra, right? These are, and this actually should be a dagger. So these guys will form an algebra. We have these guys forming an algebra together here. And this is everything else. This is what everything equals. And so this is actually very interesting. So when we apply A to our space, our Hamiltonian, to our space of Hamiltonians, or to our Hamiltonian, our eigenvalue is a decrease in this quanta. Right? This here is, if we remember, h nu. That is the quantized energy of a photon, or this is a quantized energy of a photon, right? We have this sort of same thing going on here. We increase our system by one quantized level. So we can imagine, say we have a 3-leveled system, or let's just say we have a 2-level system where our E1, here's our E1 state, and here's our E2 state. What our dagger does, this is our creation operator, is it increases by one quanta level. Okay, where A minus does is it decreases by one quantized level, like this. Okay, and this is going to lead us into an interesting proposition where we're going to want to define something called the number operator. But before I get into talking about the number operator, I want to briefly talk about these operators in the context of our quantum field theory, right? Because up until now, I've been deriving a lot of stuff, and you might have been losing me a little bit. I wouldn't blame you. But again, we have these are all operators, right? These are our operators. These guys are not operators, but actually they are, right? Because P is an operator and Q is our spatial operator, right? So everything here is an operator. So these are all our operators. We have Q, we have P, we have A dagger, we have A, we have H, we have our Hamiltonian. All of these guys are operators, and they do very specific things. They do very specific things to our states. So if we were to go back to this picture, this is where I'm going to go back to this field picture. The field picture that I've been stressing. So I've had this field picture that I've been talking about where we have some field, and we have the derivative and the non-derivative of our states, right? And we can imagine this. This is sort of an imaginary, not imaginary, or it is sort of an imaginary field, literally and non-literally, because these things are complex, where we have Lagrangians. We haven't really talked about Lagrangians yet, but we have talked about Hamiltonians. We have Lagrangians at each point, and each point here is defined by two coordinates, a coordinate psi and a coordinate psi dot. Right? And so given that, we can define a Lagrangian. But we also want to take into consideration this other picture where we have a field. We have a field, and from the field we are interested in x, t, and then we can imagine we have two other dimensions, our y and z dimensions. And we have states. Remember, these states here, these states are functions of x, y, z, and t. These states are defined by these parameters. If we know these parameters, we can define the state. Right? So we can imagine one state here. We can imagine a state right here, and then it travels through time and space to become a different state here. Here, this picture, I stressed this picture early on because Lagrangians are going to be very important. So we can imagine Lagrangians changing in this field picture. What's changing here are our states. So here the Lagrangians are changing. Lagrangians and Hamiltonians are changing. Lagrangians and Hamiltonians are changing. In this picture here, our states are changing. Right, so we have a state right here, and this state can travel through time and space, and we have a different state here. Right, so we can imagine our states being described by some vector at each location in space. Right, so that's these states again are functions of space and a function of time. Likewise, now this is what makes quantum field theory a quantum field theory, which is that these operators here, are also functions of space and time. Right, so we have, not only do we have operators that exist in here, but our operators are functions of space and time as well. So just like we had this picture here where we have our states as a function of space and time, we have our operators. So this operator here is a function of space and time. This momentum operator here is also a function of space and time. The momentum is also a function of space and time. These guys are also functions of space and time. Right, so these guys can change as we travel along space and time here. Same thing here. We have this is a function of space and time, and our Hamiltonians are obviously as a function of space and time as well. Hamiltonians, this is a Hamiltonian operator, it's a function of space and time. And this is what makes a field theory, this is what makes quantum field theory a field theory, is that for every location in space, we have different operators, right? So we've quantized space and time to hold these different set of operators. And again, these different set of operators will reach into our Hilbert space, if you will, and they will extract the necessary values and vectors within that Hilbert space, and that sort of defines what these operators are and what they do. Okay, so our picture becomes, take for example, if we could operate on a state. Here's a state. This is a function of space and time, and we wanted to operate on that state with our raising operator, right? We can actually begin to make sense of this now. This is an operator that is dependent on space and time, and this is a state that's dependent on both as well, right? So I just wanted to stress that before we get into going deeper into this, because now I want to take a look at these operators, these creation and annihilation operators, but in somewhat of a different way. I want to introduce the Dirac notation for these guys, where we're going to say that a dagger is, when it's acting on an energy state, so instead of acting on a wave function that describes a state, we can act on a vector here, a state vector that is the same thing. It's kind of the same thing. It's different notation though, and we're gonna define these guys like this. And then this guy here like this, n minus 1. So this is going to be our new notation that we're going to look at, and we're interested, and just to sort of introduce this before we get into it deeper, this here is our raising operator. It raises our energy state, or our state, to an n plus 1 state, so we increase it by 1 unit, by 1 quanta. That was this over here. We increase by 1 quanta. Okay. And then here, we decrease by a quanta. So that would be this over here. So this relationship directly is related to Dirac's notation way over here. Oops. This is related to Dirac's notation. This stuff right here. And so we're going to probe this now, and we're going to find some really, really interesting things when we take a look at these relationships. So before I move on, when I was struggling here about this negative, I think I found out what happened when this right here, this should have been a negative, because when we bring the I out here, this remains negative. All right, so we bring the I out here, we get a negative right here. That should be a negative, and now this should have been a negative. Actually, nope. I bring a negative I out, and that should fix things, because let's see, I bring a negative I out, and this should be minus. This should be a minus right here, because the commutator, yeah, because this times a negative is going to give us a positive, which is right here. So we bring out a negative, and then this here we said was I, or was negative I, so negative I times negative I, that is going to be -1. And so that's why this is a -1 right here, right? Because we said up here that this is the same relationship as this right here. So just to clear the water on that, I didn't want to say something wrong, and I hope that fixes any confusion. Okay, so we're at this point here where I'm talking about now thinking of wave functions as these wave functions right here. We're going from here, now we're thinking about them as vectors. And I can't remember now if I had talked about perceiving functions as vectors. I can't exactly remember if I've done that already. I think I have, but let's do a little refresher here. So we can think of functions as vectors, right? And we could think of them as vectors in different ways, right? So there's this idea that if we have a function, and it looks like this, we take points on our graph, and if we discretize the points, we only have a function that exists here, for example, here and here. These are going to be the dimensions of our vector space. All right, so in this case we have 3 dimensions, and the weight on each dimension is f of that point. So let's say this is x1, this is x2, and this is x3. And so this would be f of x1, this would be f of x2, and f of x3. And so we have a vector now. So here, this could be our x1 dimension, this could be our x2 dimension, and this could be our x3 dimension. And so right here we have f of x3. Here, this would be f of x1. And say this here would be f of x2. So you could think, as we increase the number of points that we use to represent our function, then we increase the dimensionality of our space, and we end up having to write vectors like this with placeholders as components instead of having to draw them out, because we can really only draw in 3 dimensions. But we could still think of vectors that have 4 components, 5 components, 6, 7, or even 1,000 components to them. They exist in this 1,000-dimensional space. We can't really draw that, but we can mathematically represent it as a column vector, for example. We can also think of some functions, like Fourier transforms come to mind, where you have a function that is made up of different functions, right? And those different functions are basis functions. Those basis functions, for example, could be basic sine and cosine waves, right? And as we overlay the sine and cosine waves of different weights on top of each other, then we get a more complex wave, right? So the complex wave is a function that has basis components, just like there's basis components here, that are that can be easily represented by just sines or cosines. Okay, and that's going to be important. That's actually going to be a very important concept in quantum field theory, because we're going to be dealing a lot with Fourier transforms. We're gonna see that kind of notation frequently come up, and I think I'm gonna plan on having that be in the next video. 1 second. Okay, and so with that being said, let's get right into some more of this raising and lowering operators. So suppose now, let's see here, we want to consider a dagger, A. We're going to act on an energy state N. And what we want to do is, give me one second, my dog's being kind of annoying. Okay. What we're going to do is we're going to say now that A, if we take these rules that we established over here, if we take these rules right here, sorry, my dog is being super, super annoying. Okay. Yeah, so if we take these rules here, so A acting on N is the square root of N, so this is the eigenvalue of A, and it takes us down to an N minus 1 state. So if we come back up here, this is going to take us, so this right here is going to take us down to an N minus 1 state. Right, so we're going to have A, this is equal to A dagger times the square root of N times N minus 1. Okay. And then we're going to have, so this is just a number. So this square root of N can come out here. Then we're going to have an A dagger acting on N minus 1. Well, if we go back here, this here is what A dagger acting on N looks like. So A dagger on N minus 1 is just going to be minus 1s on all of these. So we're going to have something that looks like this. We're going to have something that looks like the square root of N times N times the square root of N plus 1, or N minus N minus 1 plus 1, like that, because this is our N minus 1 part right here. This, and then we're adding to that, and then our end result is going to be our N minus 1 plus 1 state. So what does this reduce to? This reduces to the square root of N times the square root of N times N minus, or nope, not minus, times just N, right? And then, so square root of N times square root of N, well, that's just N times N, like that. And so this right here, this guy right here, this is what we call the number operator, right? So this right here is the number operator. So we could say that the number operator acting on N, acting on state N, looks like this, where we just bring out the value of N. So this is the energy level, right? So we can sort of picture this using Jablonski diagrams that we often see in biophysics, right? So I'll create a two-level system. Here's a what they call Jablonski diagrams, where we have, okay, so we raised our energy state, so we went from N equals, say, 0 to N equals 1. Right? So if we're starting at N equals 0, in this case, we want to end with an N equals 0 as well. Okay. And so in that case, we need to, and you know what, I actually drew this upside down because we're falling down first. You know, this was a little bit misleading, but it's okay. This is our creation operator. So we went down. This is our A operator. And then we went up like that, and that's our creation operator. So we ended up back at the original state. We started here, and we end at n equals 1 as well. Okay. And so this is how we can picture these operators, right? So let's talk about now. So I'm going to talk. So this number operator is this process right here. It's the overall process, right? It tells us, and starting from n equals 1, we could start from like n equals 2. We could start from n equals 3 or 4. If we did that, if we started from n equals 2, so here's n equals 2, or little n, to be concise. Here's little n equals 2 and little n equals 1. The process is the same, right? The process, we go from here to here, right? So this process is the same. So we could start here, we can start at 1, we can start at 2, we can start at 3. The number operator does this, okay? And what is interesting is that we can, so the number operator, n, is equivalent to this combination of operators. The number operator minus 1, we will find is equal to this combination of operators. Okay. And so we can sort of prove this in many different ways. We can prove it using commutators, for example. We can prove it using the commutator. We know that A dagger A, we said that was a real number, which was 1, right? Well, if we have n, we could have, well, let's draw this out. We could have A, so this here is A dagger A minus A dagger. And that is going to equal, that should equal 1, right? Let's see if that equals 1. So what is that? This is the same thing as n. This is n. Actually, I'll do it like this. So this should equal 1. Right, so let's see if that equals 1. So this is n, and this is n minus 1. Now you can see it does equal 1 because n minus n is 0, and this minus distributing to this negative sign right here is going to be positive 1, so 1 equals 1. Right? So this is a number. So this is called a number operator because it extracts the number of the eigenstate, and it also it also helps us in proving this point as well. We can and yeah. So this is a number operator. Right. So what's not taught, actually, and what I found to be very interesting, what's not taught in many quantum field courses is what happens if we do now something like this. A dagger. So our A dagger and we act on n. All right, so what in the world is this? All right, so we could see we have maybe we have a number operator, we have an n-1 number operator. Let's actually calculate this though, because this is going to reveal something pretty interesting that I don't think is actually taught very well in quantum courses. So let's get started. Okay, so sort of for the sake of time, I have sort of drawn this out already. So we see that the creation operator acts on the n+1 state, and this is the eigenvalue for that operation, right? This is just a number, so we can bring this out like this. Then we have our annihilation operator acting on the n+1 state, right? So that's going to bring us back down to the n state, and its eigenvalue is what was in here initially, right? So we have this is the eigenvalue of that again. We do square roots because square roots prove this relationship again through the number operator. Okay. Then we can bring that out, and then we have this, and we go to the n+1 state. So in the end, our overall picture looks like, if I were to draw our picture, we can start at the n state, and here's our n+1 state, and we start off with our creation operator, so that, or a raising operator that raises us up to the n+1 state, right? And then this is our annihilation operator. So, or this will bring us down the ladder. All right, so this is a dagger. This is A, and then extend this out a little bit more, and then we have our a dagger again. So we take our particle and we create the n+1 state out of that. So we end up right here in the n+1 state. So that checks out. We have the n+1 state, and this is the eigenvalue for this global operator here. So this, again, this is just operators. These are just operators, right? And we get the associated eigenvalue for this operator. So what we end up getting is a dagger. I'll just rewrite this: a dagger A, and then a dagger again, acting on our end state is going to give us, well, that's the same thing as just multiplying our end state by this number, n+1 times the square root of n+1, and then this is our n+1 state. So what's interesting is that this eigenvalue is actually different for different starting points. So say we're starting at n=0. So we know we're going to end up at, we know that we're going to end up at the n=1 state, right? Because if n is 0, this is going to be 1, and this is going to be 1 + 1, right? So that's going to be 2, and then root 2, right? So actually, I think I might have written this down a little bit wrong. So if n is 0, then we get a, I was putting 1 in when I was doing that mental math. So that's actually right. So that's going to be, because we have a 0, if n is 0, this is 0, and this is 0. So we have a 1 square root of 1, right? And the 1 square root of 1 is the same thing as 1, but for completion, I'll just put that right there. So, and this is equal to 1. 2 times the square root of 2, right? This is a number, this is some sort of decimal. Again, and we have 3 square root of 3, and then 4 square root of 4, and so on for for different starting points in our states. So we can sort of picture, if we were to picture this using our Jablonski diagrams, we have, say we have a 6-leveled system. Or I'll just do 5-level system. So we have our n equals 0 to our 1, and here's our 1 state, n equals 2, n equals 3, n equals 4. Right. And I'm doing this operation, which is here. So I create, then I annihilate, then I create again. And this process, this process right here, this series of operations is associated with just multiplying our vector, our 0 vector, by 1 square root of 1. Right? If we were to start, for example, I'll do a different color. Let's see what color. Let's do blue. If I were to start here at 2, right, we'd have the same process. The same process here. But since we're starting at n equals 2, then this is where we're starting here at n equals 2, then our eigen value associated with this series of operations, it looks like this. Right, and then actually I need to fix this one down here. This is not the 0 because we're ending up at the 1 state, so we're ending up at the 1 state. Right, and so we can create, there's nothing stopping us. Again, there's nothing stopping us from having some big long string of operations. So say we start at, I don't know, we could start at our energy, our 3 energy state. We can create, then we can annihilate, then we can say annihilate again. And then let's say we create a bunch of times, have a bunch of creation operators. And then like this. So this here, so we're gonna, let's see, so we create, then we annihilate, that brings us to, so if we create, that brings us to 4, this brings us back to 3, this brings us down to 2, or it's 2 state, this will bring us down to our, or this will bring us back up to 3, this will bring us up to 4, this will bring us up to the 5 state, and this will bring us up to the 6 state. Right, so what we get in our Jablonski diagram, 1, 2, 3, 4, 5, 6, no, 1, 2, 3, 4, 5, 6. We're starting at 3. We create, I'll just create a bunch of them. I'll just create a bunch of them like that. We start at 3. We create, right? Then we annihilate. Then we annihilate again. I'll extend these out a little bit. We create, annihilate, and then create again. That'll bring us back up to the 3 state, and then up to the 4 state, and then create 2 more times. And this brings us up to this is 4, 5, 6, and that checks out, right? So this is our n equals 6 state, and this is our n equals, not 33, just 3. This is our n equals 3 state. So the overall process, this is a tedious path to go through. This is definitely not the path of least resistance, because the particle could have just gone from here to here to here. It could have started like that, right? It could have started like that and just gone 3 steps that way, right? But it didn't, right? For this particular operator, we have an eigenvalue associated with that operator, right? And the eigenvalue associated with that operator, this is going to be that's going to be some number, right? So I haven't calculated that out exactly, but there's nothing stopping us from doing this process over here and figuring out exactly. This will be an equation, actually. This is sort of a function of n, right? So that this is sort of some function of n that yields some number, right? And I'll go back to black here, but we're going to have some eigenvalue as a function of n, right? And this is some function, right? I'll just make that a little cleaner. And then, so this is just a number, right? This is just a number. And then we have this is going to be our sixth state, right? This is going to be our n equals 3. So, or n plus 3 state, because we ended here and we started here. And we went through this long, tedious path of getting there, and we have a number associated with that path. So this is something interesting. We have a path, right? So if I go back to this picture here, where we have some field of states, let's see. I don't want to make this too super complicated, but we're going from, say, here's a state, and here's a state, right? A state can be represented as a vector, and we want to get to this state, right? And the vector in that place could look like that. And so the path we decided to take is this one down here. Now that could, I'm not saying, so that could maybe correspond to something that maybe looks like a path that maybe looks like this. Right. The point though is that there was a path that was taken. So we went from a path to and we associated with that path with just operating, just multiplying our original state by some number, right? And this is extremely important point right here, because when we start talking about path integrals, when we start talking about path integrals, that we want to keep this in mind. We want to say, okay, one path, a path from one state to another is associated with some value, right? This is almost like a function, right? For every point on some function, there's an associated value. So we could consider. So let's take a look at this. For example, we could say so for a particular path, we have let's see, how do I want to do this? The path is associated with, I'll write it over here, the path, it's synonymous with some number, right? And the path is a function of where we start, right? So it's a function of where we start and the series of operations. So I'll say the path is a function of where we start, n, and our series of operations, O. I'll call that curly O. Right, and that is equal to some number. And we want to take this path, we want to integrate over all possible paths, right? Or perhaps over all values of n, for example, right? So we could integrate over all values of n, which are, again, these are states, right? So the path is associated with some state and a series of operations. And the state, again, the state is a function of time and space. And so are the operators. This is what makes quantum field theory a field theory, and we'll go into that later, but the operators are a function of space and time. So these things are functions of space and time, while the path is a function of these two variables, right? This is a function of functions, right? And this is functional analysis, right? A functional is a function I'll put this over here. This is a function. It's a function of functions. A function, and its argument is a set of functions, right? So depending on what the set of functions are, we can get a functional. Right? This is akin to doing a Fourier analysis, right? Because a complex waveform, and we'll get into this deeper, complex waveform. This depends on a series of functions, right? This equals some cosine waves plus some sine waves of varying frequencies, right? And we need there's a specific set of these specific frequencies, phases, and amplitudes that'll make this guy right here, right? So we could see this all coming together, right? We could see this all coming together to formulate a field theory. The reason we call this a field theory is because these guys are fields. This is why I've stressed this picture so much. We have fields, and then we'll start talking about Lagrangians as well, where I say we have Lagrangians here. We can begin to understand how Lagrangians fit in this Jablonski diagram, right? But this is a field. This is a field. These are fields of space and time. They have values everywhere in space and time. All right. And so this video, I think, is going on long enough. The next video, I'm actually thinking about doing some more of these example calculations, but I will put that in my Patreon page for those of you who actually want to take a look at some more of these types of calculations. In the meantime, you can hold tight, and I think the next thing I'm going to want to go over is going to be putting the Hamiltonian back into this formulation, and we're going to start going over different types of operators, or different types of creation and annihilation operators that are only associated with specific types of particles, right? So we're going to be able to have these guys here. This is an operator of space and time. This is an operator of space and time, and this is an operator of space and time, just like these guys down here, where we had A daggers. And this is where quantum field theory actually gets kind of confusing, because we usually see this as a function, as a state, but we're going to have to start looking at these as operators, or these symbols at least as operators, because as of now, these things work with oscillatory, just Schrödinger oscillatory motion, right? We didn't say really anything much about photons, or having to specify anything with regards to photons or electrons, and that's gonna be the difference between. That's gonna sort of give us the difference between different types of operators, right? And I wasn't totally complete. So we had an A dagger and we had an A operator, and these things are sort of synonymous with these guys, where these guys are going to be bosonic operators. Bosonic. And these guys, these are sort of the more general type that just obey the Schrödinger equation. And then we'll have fermionic operators. And we'll see that these operators, they form an algebra together. Remember, this is the algebra, the commutator. We'll see how what these guys look like as well, right? Yeah, but wait, enough of me talking. I'll see you guys in the next one, where we will start heading towards the Klein-Gordon equation of motion, and that's gonna lead us into photons. All right, so I'll see you in the next one. Thanks.